Hi everyone, my name is Christopher Pratty and this is Dylan Weeks and Jared Hatlin, and today we're going to be presenting on the UCI cargo airplane, and our advisor is Professor John C. LaRue. So a little bit of what we're going to be going over today is how we organize the team, our scheduling, design philosophy, how we went about manufacturing the airplane, some design changes we had to make throughout the project, and then what we're planning for the future, like to help out the next year's team. So our design objective was to design and build a high-lift RC airplane that can compete in the SE AeroWest regular class competition. And how we broke down our team, we basically just broke it down into 5 different subsystems: wing, tail, fuselage, control, and landing gear. And then our scheduling was pretty much fall quarter, we went through most of the design process. And then winter quarter was when we're supposed to start manufacturing. We fell behind. So we started partway into winter quarter, and then the spring quarter, the beginning of spring quarter was supposed to be for testing and then getting ready for the competition, but we kind of fell like a good amount behind, so we didn't get to test, so we pretty much, our first flight was at the competition. So for the competition, there is a couple rules that kind of drove our design, and those were we had limitations on how much power we could provide to the motor. We had material restrictions, and then the biggest one was size limitations. So overall, we had to keep our total dimensions under 175 inches. And since we wanted to lift as much weight as possible, we put our priority towards the span of our airplane, and then we worked off of that. So pretty much we decided a span and chord that would provide enough lift to give us our target weight that would make us competitive in the competition. And then from there we decided how far our length and our height of our airplane. And then so our final configuration that we ended up coming up with was a tandem wing, which would provide us with an extra lifting surface while preserving our other dimensions. And then we had a joint wing to help reduce the induced drag and wingtip vortices. And then right here you see on the top graph is a graph that relates the stagger and the gap of the biplane and the increase in coefficient lift. We ended up coming up with a stagger of 25% of the chord, and then a gap of 75% of the chord. And we also utilized a triple rudder, which helped us reduce the overall height of the plane by splitting up the vertical tail surface. And then we implemented curtain flaps into the wings, which helped increase our lift.
So, as you can see, these are some of the flight dynamics that we kind of implemented in the plane. One of the probably most prominent things we had to deal with was the size of the cargo box, because at the SAE check-in, there's a very specific cargo box. So they have essentially a slug cargo box or cargo that they will fit into the cargo bay and make sure that fits the dimensioning required. I believe it was 6 by 6 by 14. Was it
4 by 4 by 10?
Oh, I'm sorry, it was 4 by 4 by 10. Sorry about that. We also implemented this kind of tandem wing that you can see right here, and these little circles are to kind of highlight the bracers that we use to keep the wing in place, because we were having some sort of issue where we were worried about the top and the bottom essentially separating from the cargo bay because we had such lightweight material. And we also implemented these spars with slots you can see right here, and these were essentially to speed up the design process, because last year we were having issues where ribs were not parallel with each other, or ribs were spaced not consistently. And so we were kind of using these to at least keep the overall design and weight fairly consistent, and keep at least have 2 uniform pathways. And then you can see to the right of that we have this kind of joint wing spar. And so we were using this to essentially reduce the amount of induced drag we have off of the wingtips. Unfortunately, they didn't function as well as we thought, and they tended to just more be a construction hassle. And we think that, at least from what we saw the competitive planes this year, that they tended to more just use like one sheet of either balsa or bass, whatever their construction material was. And it tended to have the same effect and be far less time intensive and far less frustrating to put together as these pieces tend to be. And then you can see above that we use slotted flaps as high lift devices. And these are essentially to help us like reduce the amount of runway distance that we would need to get off the ground and get the plane flying. And next slide, please. And so here we have construction tickets, and you can see this is essentially the completely plane without any servos or skin in place. And we primarily have to focus on elevator sizing and flap sizing so that we would have adequate amounts of lift and control. There's a big focus on rudder, like Chris said, we had triple rudder, so we had to focus on rudder sizing to make sure that we could at least pitch the plane enough so we could have control over the flight mission. And as a primary building material, we would use balsa because it was lightweight, effective, and we had a good amount of machines available to cut the pieces we needed accurately. We tended to stray away more from metal pieces, with I believe the only metal pieces being the tail boom, which is, it's in the plane right now. You can't see it because it's pretty low poly, or not poly, it's low resolution picture. But we also would limit it to the front gear and the main gear were also aluminum. But we were having issues where our configuration would not allow us to use the material we wanted. We wanted pretty sharp turns in our main gear. But the issue was we had to get the, I think we had cold rolled aluminum, and we needed to get tempered, and we didn't have I think we didn't have funding or we didn't have availability to be there to a facility that could do that for us. We were like fairly close to shearing the metal at that point with the setup we had on it. And so, at least as far as building the plane goes, we primarily were focusing on keeping clean leading edges on both our primary and our secondary wings, as well as our rudder. And what you can see here is on the right, we have an example of a leading edge sanding tool we were using which we 3D printed to help preserve the front end of the plane. Unfortunately, trying to do that was far more time intensive than we were planning on it being. And so what we're going to do next year, we hope to implement, I think 1/32 inch thick sheets of balsa that we will wrap around the front leading edge. Because this will not only save like resources, it will also probably save about like 6 hours per person working on the plane, and it will be a much more like consistent leading edge. We also try to implement as much 3D printing as we could, at least for non-structurally significant parts or parts that would at least be in retention. And what we have here is our example of this curved section to join the two wings together. We 3D printed that because that would just be way too difficult to make out of balsa. The grain didn't allow us to have a piece that would not separate under flight that way, so we essentially just made it up two joined pieces. And we kind of at least tried to use minimal machining. Most of the machining we did was just mostly laser printing, high precision laser printing.
So a lot of the stress testing that we did with our plane was using SolidWorks simulator. We did a number of tests to make sure that our design wouldn't fail in flight. We did a buckling test on the wing spars to make sure that the web wouldn't buckle under the wing loading. And this actually led us to adding an additional web down the center of the wing spar to help stiffen it up a little bit. We did drop tests for the landing gears, which actually proved that it wouldn't yield, but it would deflect too much. So that ended up leading towards our landing gear stiffener, which Colin and Joseph both helped us with, and we'll talk about that later. We did static testing for the wing loading as well as mobile tests for the wings and the overall structure of the plane, both for low frequencies, just for fluttering during flight, as well as high frequencies for the motor. Seon, who is not with us, did a lot of CFD analysis for our wing tips, and they did reduce So we added a wire and spring between the two legs of the landing gear, and that really helped stiffen it up and give us the strength that we needed out of it. And then a real last minute change at the competition, we decreased the aspect ratio. We put a huge emphasis on drag, certainly more than we should have. The flight pattern we have to fly is very small. It's just one lap. We could really just run the motor and drain the battery, and it would be no consequence to us. And then that would give us better wing loading. You know. Anyways, sorry. The wing incidence angle is something that we had kind of overlooked. We did not build an incidence angle into the plane itself, and so while it was sitting on the runway, it was at a 0-degree angle of attack, and it was not enough for us to really rotate on takeoff, and that was something that we had to change at the competition in order to get up in the air at all. As well as some manufacturing techniques. Not a lot of teams use stringers. Most of them just had a very close rib spacing and just used that for skin support, and it made it much easier to access wires or things that were broken. You wouldn't have to cut away stringers and then replace them. Lighter wheels, a lot of teams had either laser cut wheels out of plastic or other wheels of their own design. We used inline skate wheels, which were very sturdy and very durable, but unfortunately very heavy. And then material selection, we really tried to use balsa everywhere we could, but that didn't always seem to be the best option. Aluminum spars seemed to be a popular choice, and it really would have paid off in just saving time in manufacturing as well as strength and durability. So this is us at the competition. We really learned a tremendous amount in the last maybe 3 weeks of the building process, and probably double that at the competition itself. And so we're really going to put an emphasis on documenting this for our future teams and really trying to bring a lot of the knowledge that we gained this year into our team for next year, so that hopefully they'll have a little bit better understanding and a much better head start. So, any questions?